Hello guys, it's time to test my little robot out before I start making a pen for it. I don't know if you can see here, what I've drawn is a circle. There's three circles. This is where the pen, if it was drawing, would travel along the middle bit. And these are the outer and inner, so these are where the wheels will follow. So the two wheels. I've made a little box to place my little robot in there. So yeah, that's to go in that box there. Line it up best I can. So you can see that one wheel should be following this line all the way around. Badly drawn. This board I've got is bent and it's got. I need a better board. So I'm not expecting it to be accurate because of all the. I've had this. I stored it on top of a radiator and it's just messed it all up. So, anyways, and this other wheel here, this one should follow this inner circle. So what I'm going to do is just send two commands, one to this motor and one to that motor, and then my driver, the board, my driver board, should then control the two wheels so that they run at a set RPM for a set distance. Now I've done a document to try and explain this, so let me just bring that document up. Here we go. Well, I'll tell you what, make this really big to start with. Yeah, so differential drive circle calculation. So everybody knows that the cars, well, actually modern cars, well, electric, well, the two drive wheels on your car, they have a differential, so the wheels can move at different speeds. So we're sort of like doing it in reverse. What we're doing is we're calculating what the speed each wheel turns and how fast they turn when turning around a circle. So that's why we call it, that's a differential drive circle calculation, because basically you've got there's a differential between these two wheels. Like I said, this wheel will follow this blue line. This wheel would follow this other blue line, and the pen, if it had a pen, it would have drawn this green line, basically. So my distance between the two wheels is 106. I meant to make it 100, but I must have got a 3mm wrong somewhere on the thickness of the material. Anyway, so it's turned out 106, but it doesn't matter because we just measure that and we calculate using that dimension. So the midpoint is 53 in between, so yeah, half 106 is 53, so that's that. And I want it to do a 200mm radius, so that's this radius that we're talking about, the green one, 200. So this wheel travels on a radius of 147, and this wheel travels on a radius of 253. So we use these numbers to do our calculations. So that's basically what I've just said. And so basically we can each wheel path distance, we can calculate that. So basically we use a formula: circumference equals 2 times pi times radius. And that's how far the wheels have to travel. It's these. So if we look at the outer wheel, it's got to go, believe it or not, 1 meter, 1.5 meters. So even though this radius here is only 200, to actually travel around there, that's 1.5 meters going all the way around that bit. So that's what we've just calculated there. Now we need to convert them to ticks, because on my I don't know if we can see this. Right, see if I can zoom in there. Yeah, that's it. Right, so my motor here has an encoder on the end, and it's this encoder that gives ticks. As it turns around, it goes tick, 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 tick. Well, it's magnetic and what have you. The data sheet says it's 7 ticks per revolution, but I sort of measured it on my multimeter, on my oscilloscope. In fact, actually, I'll just show you how I did that, because you need to know how many ticks per revolution this motor does. Although it is pretty much irrelevant, because what we're going to do is calibrate the ticks to the wheel and how the distance travelled. So let's just go back to that. So what we need to know is how far one tick is from our motor. So we send a command. Let's make that a little bit smaller. There we go. We send a command to our robot, and we send it in a straight line, and we set it at a certain amount of ticks, so that well, basically what we do is I'll send this command, say 70,000 ticks at whatever speed we want, and it will travel that many ticks. And then what we do is we measure from the start to the finish, and that gives us how many millimeters per tick. So if we send it 70,000 ticks and it travels from here to here, and that distance is 413 millimeters, then all we do is do our calculation, which is ticks per millimeter. We sort of like divide one into the other. I haven't written that down, that conversion. I must have removed it. Yeah, so 7,000 ticks equals 413. So ticks per millimeter, we sort of divide 70,000 by 413, and that gives us this per millimeter. So we can use this number as a multiplier for our millimeters that we're using here. So once we've got that, well, that's our calibration. Oh, there we go. Compute ticks is per millimeter is ticks divided by millimeter. So there we go. I did write it down. So then we have to convert the distance to ticks. So we worked out how far the outer wheel had to travel, and so we just multiply that by that many ticks, which gives us that. It's a 0.4, but a tick is a tick. There's no fraction in ticks, so we need to round that number up, that point. So we give it 6943, 453 ticks. And the inner wheel, we know it has to move that distance, so we multiply it by this number again. That gives us that number of ticks it's got to travel. So now we've converted millimeters to ticks. So my actual driver board for the two motors knows how many ticks each wheel has to travel. Then comes the RPM. So we have to set the speed of both wheels so that they actually start and they finish at the same time. They both have to finish at the same time, otherwise the robot's just going to go spin round in circles, I think, on the spot. So to work out the ratio is simple, really. We've got 147 and 253. We divide one by the other. These are the radii. So if we look at here, we've got this radius and that radius. It's proportional. The speed that these have to go, the RPM, is the same proportion as these two here. So we divide one of these by the other, and that gives us the difference in radius. Obviously the outer one is going to go the faster speed. We know that, it's got further to travel. So that's our set RPM that we use. We use the outer one as the ruling RPM. So once we find the radius, we decide what the outer wheel is going to go at, and so we use the outer. Say we're going to set the outer wheel at 10,000 RPM. Then we work out the inner one by using this ratio. So we just multiply 10,000 by this, and it gives us this. So that gives us our inner RPM. So then we just have to convert that into commands, and the commands my driver board. Let me just bring up my GitHub page. Right, this is my GitHub page for my motor driver version 2. There was a version 1 which is superseded now by this version 2. It looks like this. I didn't do a picture of the one, but anyway, this is basically, you can just send it down I2C, and you can control 2 motors with each board. So, well, you can have a look at this page if you. But I've updated it, so the code now for this latest version, I've done a version 3 firmware, so it's version 2 board and version 3 firmware. And so the changes I've made, as a general rule, I've put all the commands here that can be used. And so what we're using is a go-to command. So we use the GO to stop, the G1 to send it to a actual position. The position is the ticks, the number of ticks, and the speed is the RPM. My board does 2 types of RPM. Well, it 2 types of speed. In the go-to mode, it uses the value as RPM, and then we've got a basic mode where it uses the speed, which is a PW duty cycle, so that's 0 to 1000. So this one gives you, you just see it is forward or reverse, basic, and at a fraction of the voltage to the motor, basically. But in the go-to movement, I have added PID so that we can actually set it to a actual RPM, and this is the command that we're going to use here. Do an example. Yeah, so that's like a basic, which will be 75 duty cycle. This is the go-to command, the G command. And it makes, so to move motor A to a position 2000 at 500 RPM, this is the command that I would use. So yeah, so what we do is we've worked out the number of ticks. So the P value is the number of ticks, and this one here for motor B, the inner wheel. And then we know the speed, which is the RPM, 10,000 RPM, and the speed here is 55,818 RPM. And then we send them to. So shall we give that a go and see what happens? So I'll just get rid of that. So what we need to do is turn it on, fingers crossed. Yep, connect them two together. Wrong glasses on. I've got that the right way around. Can't see what I'm doing. Just hang on. Oh, it's upside down. There we go. Oh, there we go. That's it. Right. Good job. You can only put it one way. Can't see what I was doing there. Right, so we've got that turned on there, and so what I need now is my serial monitor. So bring up my serial monitor, and as I say, I've changed this so I can actually send more than one command. Oh, we need that. Well, I've written it down. Where are we? Was it that one? No, it wasn't. It was. Hang on. Where's my what we're looking for is them 2 commands there. So I want oh, I've done this. Got it all ready. Right, let's. Oh, there it is. There we go. Oh, yeah, I've written there, circle. Oh, my memories. So let's connect. So we connect, and it's connected. That stopped flashing, and so when I press, let's just make sure we're at 0, 0. So let's do an X. Just check where we are. Right, so we're at, it's set at 0, 0. Good. So where have I written circle there? So what we need to do is we need to send that one and that one. So that's one wheel and that's the other wheel. Yeah, let's go for it and see what happens. Send. Panicking. Go on, send. There we go. Oh wow! Yay! That looks good, does that? That just looks like I expected. So basically, all I've done is just send them two commands, and it's now drawing that circle. There's no segmented bits or anything. It is just drawing a circle. The two wheels are moving at their respective speeds, and hopefully when it gets back to the box where it started, it should stop. Bang! Both motors stopped at the same time. That was fantastic. Right, let's try that again. It's not quite right. Right, so let me just bring my notes up. I want to explain something. Yeah, so bring my notes up. So we've got that, we've done that. So mechanical accuracy. So some notes. So it's going to be active. So if there's any wheel slip, well, you can see how bumpy it is and what have you. It's got to go over that joint. So that's going to make some difference. Tread deformation. Well, there's no going to be. It's hardboard. I've laser cut the hardboard. It's a solid piece of hardboard. But then there is a backlash. Now that could play a thing. What we can do. So now it's actually. Well, I'll come to it in a minute. Belt elasticity. Well, no, that isn't a problem. We're using a timing belt. So because we're using a timing belt, there's going to be no stretch and pull on that. Basically, it's quite a tight fit. But then there's surface friction. So surface friction, if it, like I say, that's pretty much the same as wheel slip and wheel damage. Well, we haven't got a problem with that because I've laser cut both, and they're both exactly the same diameter. But what I could have done maybe is, this is the reason why I made these a really tight fit when I was assembling it, is I didn't want any misalignment with the wheels. If the wheel has a wobble or misalignment, that's going to affect my travel as well. And because we're moving quite a fair distance, it's going to build up that. So yeah, move that. Bring my serial monitor back. And what we can do, that there is also, because we were moving at this motor was spinning at 10,000 RPM. That's quite fast. There could be overrun, which we need to compensate. So what I could do, so if we just do an X command and send that, we can see where it actually finished. So what we wanted is we wanted 269. Oh, that's wrong, is that? Because I remember, yeah, we were rounding to 1,000. That shouldn't have been that. That should have been. Yeah, it should have been these values here. So what I need is, can I copy that? 269. Yeah, it's been rounded. That I forgot all about that. Change that to that, and change that. Change that to that. So actually, Didn't it come? Press it, wrong button. Right. Right. This one. Copy that. That should have copied. Oh, copy it. All right. I'm going to write that down. G01 D 156 547 547. There we go. Right. So they're the ones I'm going to send. But so we're actually at 29155. So it's not quite where I wanted it. Well, there should have been zeros anyway, but using the last command. God, I'm rambling. So what I'll do is I'll just try again, and then I'll come back to what I was about to say. So what I'm going to do is I'm just going to line this back up with the box. It isn't quite aligned. It's not quite in the exact same position it started from, obviously because of the variables that I mentioned. But those are things to iron out once we're happy or we're on the right track, shall we say. So what I'm going to do is I'm going to set these two to 0 first. Go here, that one there. We send that a signal. If I inquire at what position we're at now, that should be 0 0. So yeah, we can see 0 0. So what we can do is now use the circle command with the correct positions and see what happens with that. So let's give it another go. Send them. Yeah, you can see it bounce over the top of that one, couldn't you? That wasn't going to help it keep straight. Right, so what we can do is check where it actually finished. So if we do an X, see where it actually is, we can see that this is its actual position. That's the position of these two motors. And we can see that our circle here, so this was 269543 and 26618. So we can see that we've got a mismatch there. We're not actually in the same position, in this position that we wanted. So we've done a slight overrun. But what we were doing, we was doing this at the max speed. So what I can do to maybe overcome this is if we go to these two commands, but what I'll do is I'll half the RPM. So let's go 5,000. I've got there 58. Oh, my brain's dead again. 5800. Yeah, 2900. Right, so let's make that one 2900. Like that. And if I send that, that should just maybe put it closer to where it should be. There. See how it just did a little wiggle to come back. I sent them, so let's just do another check now with the X, and if we look at its position now compared to 269453, we're getting closer. I mean, what I could actually do is halve the speed again, half the RPM, and it wouldn't overrun as much. But that's something to add into the code when we're actually commanding it through some script, basically. But yes, I think this has turned out rather well, and it's actually done what I wanted it to do. So it's not, well, let me just measure that. I mean, it should have been back in its box here. Well, right, so move that out there. So I'm not going to measure from where this box was here, from that line to that line. And we can see that it's actually about 20 mil. So there is some sort of, I need to get a better board for it to run round on, and maybe I don't know whether to add some rubber tyres onto these wheels and make it a bit thinner, and just glue some like rubber bands, you know, rubber belts that you sort of get on small items, and maybe that'll stop the slip, and hopefully the friction will cancel each other out on either side. But yeah, I'm quite pleased, guys. It's done what I had in my head, and that is drawn a circle. But like I say, getting over friction and things like that is a real hassle to do. So what I'm going to do is I'm just going to set that as 0 again. So we'll just go with that one. 0, and then we'll do the 2 circles, and we'll watch it go for one more time. Yeah. I think that jerkiness is my computer not being able to draw the video. You know, I'm getting a lag in my video, I think, and maybe I'm running too much at once. But I like what it's doing. I think this is a win, guys. I mean, it's not as accurate as I wanted, but I think it's a big win, is this. There we go. Okay, I hope you found that interesting, and thanks for watching. Catch you with the next one.